Welcome. You've tuned in for a quick but pretty comprehensive look at something truly fascinating. Neuromorphic technology.
Yeah,
Think of this as your rapid immersion, sort of getting you up to speed on a field that's really buzzing with potential and, well, moving incredibly fast.
that's right. Today we're digging into the current state and maybe more importantly for you, the future commercial prospects of these, brain-inspired computing systems.
And our main guide for this deep dive is a really great article from Nature Communications. It's called The Road to Commercial Success for Neuromorphic Technologies.
Yeah, it's a fantastic piece.
Really lays things out clearly.
Absolutely. It maps the landscape beautifully.
Mhm.
So, for anyone maybe hearing this term for the first time, neuromorphic technology. Well, at its heart, it's about building computers that mimic how biological neural systems work, like your brain.
Exactly. Your brain is just incredibly efficient, right? Always processing stuff in real time, communicating with these tiny, sort of sparse bursts of activity.
Mm.
Neuromorphic tech is aiming for that same kind of efficiency, that continuous real-time operation, and what they call sparse event-based communication. It's a real aha moment when you realize, wow, we're taking cues directly from biology.
And what's really interesting and kind of the core of our discussion today for you is that the article argues that after some, let's say, initial bumps in the road,
Ah.
neuromorphic tech is now really showing strong promise for, widespread commercial adoption.
Right. So our mission really is to understand why that shift is happening now, what problems got solved, what's paving the way for this stuff to actually end up in, the technology you use every day.
Precisely.
Okay, let's unpack this. Where did this whole idea even start? Neuromorphic computing. Sounds pre-futuristic.
Well, if you think about the big picture of computing history, neuromorphic architectures are kind of being seen now as this third major pillar.
A third pillar. Alongside what?
Alongside the classic von Neumann architecture that's your CPU and the tensor processors, GPUs, TPUs that are so huge for machine learning now.
So you've got the standard CPU workhorse, the GPU number cruncher, and now this brain-like thing, a third option.
Kinda, yeah. And the inspiration, it goes way back. The article reminds us, and it might surprise you, people like McCulloch and Pitts were thinking about simplified neural units ages ago. Turing, too, ideas about self-modifying systems.
Wow.
Even von Neumann himself, the guy behind the architecture we still mostly use, he was apparently really interested in how the brain computes.
That's wild. You don't typically associate von Neumann with, like, biological inspiration.
It just shows the brain's allure as a computing model has been there for, well, the brightest minds right from the start. Now, the core elements of neuromorphic tech today, they echo biology directly for you.
How so?
Things like temporal integration, how signals build up over time, using multiplication with really low precision, sort of like neurons might interact. And this idea of thresholding.
Thresholding.
Yeah, a neuron only fires, it only communicates when it hits a certain activation level. It leads to this binary on-off communication. Very efficient.
Okay, so instead of step-by-step instructions like normal programming, it's more like these connected bits reacting to signals over time, kind of like a real neural network.
Exactly.
Yeah.
That's a key difference for you compared to the usual procedural programming, von Neumann's fetch and execute cycle.
Yeah.
Neuromorphic is much more parallel, much more event-driven. It only computes when something changes.
That sounds efficient. It reminds me a bit of how GPUs took off.
How do you mean?
Well, it started with graphics, right? But then people realized that parallel power was perfect for machine learning, for all that data. It changed everything for image recognition, stuff you see now.
That's a brilliant parallel, and yeah, the article draws that exact comparison for you. GPUs found their, let's call it, killer app in data parallel problems like neural nets.
Right.
And NVIDIA's CUDA platform, their API, was absolutely key. It let developers actually use that power.
Okay.
And deep learning itself provided the programming model, a way to map problems onto those parallel chips, made them accessible to people like you indirectly.
So deep learning gave GPUs their language for new tasks that affect your life now.
Got it. Now, the article mentions early forays and challenges. What were those first steps, and why didn't they immediately, succeed for everyone?
Well, the article points back to the 60s, Carver Mead in California, really focusing on mimicking neuron dynamics in silicon. That was the start of neuromorphic engineering.
Okay.
And we did see some early commercial wins, things you might even recognize, those early touchpads on laptops, optical mice sensors, even some low-latency vision sensors still used today. Those have neuromorphic roots.
Right. So sensing seemed like a good fit early on, but what about the actual computing part, processing information?
That's where it was slower, commercially
Yeah.
speaking for you. Big names got involved. Qualcomm had Xeroth, IBM had True North, Intel had Loihi. These were really cool event-driven chips.
I remember hearing about some of those.
Yeah, but as the article notes, most of those efforts, well, they've shifted focus. Intel's still pushing Loihi, and IBM's doing interesting stuff with memristive computing, but Qualcomm, for instance, moved on. So initial excitement, big players, but then it stalled. Why? What was the barrier for you seeing these chips everywhere?
A really key challenge early on was just uncertainty. Nobody was quite sure which bits of brain computation were the most important to copy for solving real problems for you.
Ah, okay.
So you ended up with these chip designs that were incredibly flexible, trying to cover all bases, but that made them super complex to understand and program.
Right.
And critically, there wasn't a good general-purpose programming model. It was like having this amazing, intricate machine.
But no instruction manual.
Exactly. No easy way for developers to make it do a wide range of useful things for you. But, and the article stresses this for you, don't get bogged down by those past complexities. Solutions are emerging now.
That's good to hear. So what was the turning point? What changed to make commercial success, well, more likely and relevant to your future tech?
The real game changer, the article argues pretty strongly, has been the development of neuromorphic programming models, especially since about 2016.
Programming models.
Okay.
Before that, getting an app running on a spiking neuromorphic chip.
They say it could take like a PhD's worth of effort.
Wow. Okay, not exactly developer friendly for creating technologies you'll use.
Not at all. It wasn't just writing a bit of code.
So what were people trying before that? These earlier programming attempts, why didn't they work out sooner for you?
There were a few approaches. You had people literally hand-wiring networks or using learning rules like STDP, spike timing dependent plasticity, directly inspired by how brain connections change.
Okay.
Those could work for very specific, narrow problems, but not general stuff, not the diverse computing challenges you see.
Too specialized.
Right. Then you had ideas using random architectures.
Mm-hmm.
Theoretically powerful, sure, but practically hard to guarantee they'd work reliably, often inefficient. They mentioned meeting teacher dynamical systems, which isn't always practical for you in real application development.
Doesn't sound easy.
Modular networks were another step, building complex functions from smaller spiking blocks. Better, but still kind of limited in scope for you.
Sounds like a lot of dead ends, or at least not the main highway.
Kind of. What really cracked it open for you was applying gradient-based machine learning optimization.
The same stuff that powers deep learning, like the AI you might use daily.
Exactly the same fundamental idea. The breakthrough was figuring out how to adapt it for these spiking networks, using tricks like surrogate gradients, backpropagation through time, even calculating gradients directly from spikes.
Okay, that sounds technical, but what does it mean for making these chips useful for developers and ultimately for you?
Think of it like this for you. Suddenly, you could train these neuromorphic systems using familiar tools, data sets, loss functions, just like standard deep learning that powers so many AI features you interact with.
Ah, okay.
This meant you could train huge spiking neural networks for really complex tasks. The article mentions things like large language models, autonomous driving, stuff that was pure science fiction for SNNs before. That's the big aha moment for you.
So, the methods that made deep learning so powerful, leading to things like good voice assistants you might use, could now be used to teach these brain-like chips.
Precisely. And as a bonus, this approach can even help compensate for some of the imperfections you get in analog hardware, making the whole thing more robust for you.
Wow.
But the absolute key takeaway, this gave neuromorphic computing a general-purpose programming model for the first time. Suddenly, deploying applications got way easier, faster, more convenient for developers. That's what opens the door to widespread use in products you might actually own.
That sounds like a massive leap. But okay, the article then talks about the path to commercial success, not just being about the tech. What else needs to happen for you to see this in your devices?
You're spot on. The article really hammers this point. The competition isn't just other neuromorphic chips, it's the standard commodity devices you already have.
Right, like the chips in my phone or smart speaker.
Exactly. So to succeed commercially, to get integrated into your life, neuromorphic tech has to offer clear, compelling advantages, better cost, lower power, new capabilities. Something that really makes sense.
It can't just be novel. It has to be genuinely better in a way that matters to the market and benefits you. So where's the market interest? Where do these chips really offer an edge that could impact your future?
Well, the article contrasts those huge, expensive brain simulation projects, cool research, but limited market, with the absolutely exploding market for machine learning inference on portable devices.
You mean like tiny ML, running AI right on the device?
Exactly. Tiny ML in-home devices you might have. Moving that computation to the edge, away from the cloud, has huge pluses for you. Privacy, security, reliability if your internet drops out.
Yeah, that makes sense.
And this is where neuromorphic tech fits perfectly. The demands of tiny ML, low power, small footprint, real-time processing that's Neuromorphic's sweet spot.
So less about building giant artificial brains, more about making our everyday gadgets smarter and way more power efficient for you.
That's the focus. The article points to really promising niches that could directly affect your life. Things like low-power sensory processing, better human-computer interaction,
Like what specifically?
like audio or visual wake words, so your devices respond instantly without draining battery. Voice and gesture control for your smart home that just works. General situational awareness, maybe a device understanding ambient sounds for safety, or detecting presence to save energy, or even understanding basic behavior for more personalized experiences for you.
Those all sound like places where being always on, but using hardly any power would be a huge win for battery life and responsiveness in devices you use.
Mhm.
What about the engineers, though? The people actually designing the stuff into products you buy? How easy is it to work with?
That's the whole ease of use and interfacing point. It's critical for you to see this tech widely adopted. Engineers need flexibility, easy integration,
Meaning?
meaning standard digital interfaces, SPI, I2C, common stuff, standard voltages, small packages, all the practical things that matter in real product design, and affect cost and availability for you.
The nuts and bolts.
Right. And again, that deep learning style programming model with familiar APIs, that's huge for making it easier for existing ML engineers to adopt it and build apps you'll find useful. Plus, they mentioned the need for good software tools, tutorials, workshops. Building that developer community is key for creating the products you'll eventually use.
Now, make it feel familiar, make it easy to integrate. That seems crucial for you to get the benefit. What about reliability? Weren't there some worries about early neuromorphic chips being a bit flaky?
Yeah, that's the reliability and robustness section. Super important for tech you rely on daily. There were concerns both about whether spiking networks could actually handle complex tasks reliably and about mixed signal or analog hardware having inconsistencies, mismatch of manufacturing.
Okay.
But the article explains that the newer generation, often simpler, inference-only chips, built using standard digital CMOS processes.
The same stuff used for regular chips in your phone.
Exactly the same reliable, high-volume manufacturing. That largely solves those reliability and robustness issues, which is vital for mass deployment in consumer gear, where you need millions of chips working consistently for you to have a good experience.
So sticking closer to standard digital manufacturing helps ensure that consistency you expect.
Precisely. Then there's standardization and benchmarks. Maybe not the most glamorous topic, but really important for you as a consumer.
Why is that?
Well, standardization makes things work together. Benchmarks let you compare performance. The article says standardization has been slow, but we are seeing new open-source software frameworks emerge that fit that deep learning model. They mentioned Rockpool, SNABS, Spiking Jelly, Norse.
Okay.
These tools help developers build things more easily, and they enable benchmarks so you can actually compare System A versus System B fairly. Helps you know you're getting good value.
Benchmarks are crucial. So what are the results? Are these chips delivering on the low power promise in comparisons?
Yeah, the article highlights some really promising numbers suggesting real benefits for you. For SNN inference, they're seeing big energy savings over GPUs, other edge AI chips, even Raspberry Pis.
Meaning longer battery life for your gadgets?
Potentially, yes. Analog compute and memory shows huge energy wins in specific tasks, like physical simulations compared to CPUs, GPUs.
Mm-hmm.
Even on standard AI tasks, like image recognition, some neuromorphic approaches show better energy efficiency and compute density.
Denser compute means more power in smaller chips.
Right. And for things like keyword spotting, letting your smart speaker wake up in the power savings can be massive, orders of magnitude better than traditional processors. That means more responsive, efficient devices for you.
Wow, okay. So the data is starting to back up the claims, real-world benefits that could translate into better products for you.
Exactly. And the article argues we need more industry-standard benchmarks focusing on these edge tasks to really drive home the value proposition for technologies you'll use. They even float the idea of hardware standards, like agreeing on a common neuron model like the leaky integrate and fire neuron. That signals maturity to industry, makes life easier for developers, and ultimately benefits you.
It sounds like they're really trying to learn from what worked elsewhere. You mentioned NVIDIA and COMB before. What's the lesson there for neuromorphic success for your benefit?
That's a central point. NVIDIA had the magic combo. Intensive deep learning models needing power, gradient-based training, making them trainable, and that relatively simple early CADA API.
Right, the tool to unlock the hardware.
Exactly. It let developers jump in, build bigger models faster, leading to AI breakthroughs you now interact with, which drove huge demand for NVIDIA's hardware. The lesson.
Mm.
Simple programming models, easy API access. That's gold for adoption by the developers creating apps you use. So the recommendation is for the neuromorphic community to really back and consolidate the current open source tools, get them to industry standard quality,
Mm.
make it easy for developers to build the next wave of smart devices for you.
Make it easy, show the benefits for you, and adoption will follow.
Got it. So let's talk hardware you might actually see. The
Right.
article mentions a commercial renaissance. What kinds of companies, what kinds of chips are appearing?
It's quite a mix now. Big established players, smaller startups, lots of activity, all aiming to get this tech into products you might use. The article even includes a figure showing this ramp up. And it talks about this interesting overlap between analog compute and memory and event-driven computation. What's that about?
Right, analog compute memory, or CIM. It's this idea of doing calculations right where the data is stored, in the memory itself.
Why do that?
Huge potential for energy savings and density. Less shuffling data around
Hmm.
means potentially more powerful processing and smaller, cooler chips for your wearables or IoT gadgets.
Mm.
And mixed-signal neuromorphic chips often use analog signals anyway, mimicking neurons. These can interface nicely with analog CIM outputs, maybe skipping some conversion steps, saving even more power for you.
So cleverly combining ultra-efficient memory with brain-inspired processing for maximum power savings in your future devices.
That's the idea. They discuss different CIM technologies, flash, ReRAM, each with pros and cons. CIM looks great for efficiency and density, but it still has challenges. Throughput might not match standard AI chips yet. Scaling up is hard, and dealing with that analog device mismatch is tricky for ensuring reliability for you.
So imperfections in the analog parts.
Exactly. Digital neuromorphic chips, on the other hand, are easier to make reliably using standard processes like your phone's CPU. They avoid the mismatch problem, giving more predictable performance for you.
So it's a trade-off. Potential peak efficiency with analog versus the proven reliability and scale of digital for bringing neuromorphic computing to you.
That's a great way to frame it. And the article points out that inference-only chips are a good fit for commercial deployment in products you'll use.
Inference only, meaning they just run the AI models, they don't train them?
Correct. Training is done elsewhere, then the model is loaded onto the chip. This simplifies the hardware, cuts power, makes it cheaper for mass production. The focus for these chips is really edge IoT, real-time workloads right inside your devices.
Okay, so these are the chips likely to power smart features and watches, sensors, home devices, the stuff becoming part of your life.
Precisely. And getting them deployed at scale, really impacting the tech you use, requires thinking about a lot of practical stuff. Like easy interfacing with standard hardware, using common protocols like SPI-I2C, being able to run independently for critical tasks, minimizing size and power for small gadgets, making them easy to program and update with new features you'll want.
All the stuff needed to make it just work reliably for you.
Right, and they note that while current chips hit some of these points, no single device does it all yet. There's still room for innovation to create even better products for you.
Sounds like there's still engineering work needed to make these advanced chips truly plug and play for the devices you expect.
Absolutely. Now, the article revisits that classic question, the hunt for the killer app, the one big thing that makes everyone need neuromorphic tech.
Right.
But it reframes it in a really interesting way, I think maybe more useful for you to think about.
Oh, how so? Not looking for the one big disruptor that makes you need neuromorphic tech overnight.
Exactly. They argue the better question for understanding the impact on you is, which applications and processors can be enhanced by neuromorphic compute?
Enhanced, okay.
And they point straight at that booming IoT and edge sensing market. Neuromorphic is just tailor-made for ultra-low power processing right next to the sensor. They give examples you might see. Super efficient voice activity detection in microphones, or vibration sensing for monitoring machines, or maybe even appliances in your home.
Yeah, areas where low power is critical for battery devices you use, and continuous sensing is valuable. Seems like a natural fit.
Totally. They also mention wearables and portables you might own. Offloading sensor tasks to a neuromorphic chip could drastically boost battery life, enable continuous health monitoring ECG, EEG in fitness trackers, better wake word detection, understanding the acoustic scene around you, all using less power.
Making your devices smarter and longer lasting.
In-camera processing is another one, smart analysis with low power draw. Think smarter security cams or phone image processing. Again, they stress simple, standard interfaces are key for adoption in products you'll buy.
But what about the killer app? Do they just dismiss the idea that there isn't one single thing that will drive it for you?
Their conclusion is actually pretty clever. It shifts the focus entirely. They argue that the new ML-inspired neuromorphic programming model and the APIs are themselves the killer apps.
Whoa, okay. So the tools are the killer app. Not one specific use case, but the ability to easily build many useful applications for you.
Yes, because these models allow for targeting almost any application. They let developers build bigger, more complex neuromorphic apps to solve harder problems for you. And they massively speed up development for the engineers creating your tech.
Right.
Combine that with simpler, inference-only chips. And suddenly, neuromorphic tech feels familiar to ML developers, but still keeps its huge advantages in energy efficiency and power for all those IoT, wearable, and edge devices you'll increasingly use.
So it lowers the barrier to entry for developers, letting them leverage the benefits across the board for you.
Exactly. They even think this new approach could help older analog designs, allowing software to compensate for hardware quirks, maybe breathing new life into earlier concepts for applications that benefit you.
So it's about empowering developers across many areas, enhancing your overall technology experience.
Precisely. The article finishes with clear recommendations. Consolidate those open source tools. Make them robust for developers building your tech. Standardize benchmarks relevant to industry so you can compare fairly. Engage with existing ML benchmark groups. Focus commercial efforts on wearables, edge, IoT sensors where the benefits for you are clearest.
And for researchers.
Focus on mass production challenges to make it affordable for you. Contribute to those tools and benchmarks. Make building commercial applications easier so more useful products reach you. And, importantly, get neuromorphic methods into training courses to build the workforce needed to innovate for your benefit.
Sounds like a roadmap for the community to build on these breakthroughs and really deliver value to you.
Absolutely. The final takeaway for you is this exciting convergence. Brain inspiration meeting engineered optimization. And the timing seems right to capitalize on it for widespread success that will really impact the devices and services you use.
So, for you, the listener, the big takeaway today. Neuromorphic tech isn't just lab research anymore. Thanks to these new programming models, it's a viable, promising alternative, especially for all those smart edge devices becoming part of your life.
And maybe a final thought to ponder. With this potential for ultra-low power, specialized computing, how might it fundamentally change the design of your everyday devices? How might it change your interaction with technology? Think beyond today what's possible when devices can sense and react in a truly brain-like way, enabling more intuitive, efficient, maybe even more personal experiences for you.
It's definitely an exciting road ahead. The possibilities neuromorphic computing unlocks seem really compelling and could genuinely shape the tech you'll be using soon. If we've sparked your interest, hopefully you now feel equipped to explore further. Thanks for joining us for this deep dive.